What we're doing is chapter 9, and this has to do with the structure of the atom. We've already talked about some basic information about the structure of the atom, but here we're going to go into the details. This covers, touches on quantum mechanics and the orbitals of the atom. So the first part here, 9.01, is pretty straightforward, but 9.02 involves some really deep um, concepts, and it's going to be difficult to grasp what's going on. So um, I'm going to start light with this right here. Remember, this is not part of your midterm, so don't worry about it too much. Just sort of digest it, and then probably when you're less stressed about your midterm, you can look at the video and review what we've talked about here. So let me go ahead and start. What we have is EMR. EMR is electromagnetic radiation and the hydrogen atom. The reason why we are talking about the hydrogen atom is because the hydrogen atom is the simplest element out there, and we pretty much learn about atomic structure by investigating the simplest element out there. So part of the questions that we're going to ask in this section, and hopefully you guys will have an answer at the end, is what are the components of light? Light is not just something you take for granted. It actually has scientific component. How are the electrons arranged in the atom? And you guys have that idea already from the previous chapter, back in chapter 6. Um, what is the relationship between light and the atom? We actually use light as a tool to figure out the structure of the atom. Okay. How does light give clues about the structure of the atom? And you'll see that in this discussion as well. How is it possible to determine the chemical composition of the sun? And that's part of our discovery about the components of the hydrogen atom. So you guys did this experiment earlier in the semester, the flame test, and you remember that different elements give different colors of light, and it goes back to their atomic line spectrum. And it has to do with how the electrons are arranged in an atom and how they go up to an excited state. And when they relax back down, they go through different pathways that gives rise to these light. So hopefully you guys will make sense of how these right here, of the light of certain chemicals, okay, the light of certain chemicals are going to give rise to a unique atomic line signature. So electromagnetic radiation is simply that. It's called electro. It's got two components. It's got an electrical part and a magnetic part. And radiation just tells you that it's a form of energy. So, in fact, almost all our energy that we get here on planet Earth is from electromagnetic radiation from the sun, all except nuclear energy. So here's an illustration of, say, we have sunlight over here, and we look at one beam. And if we look at that one beam and we dissect its component, there's a wave, light is a wave, and orthogonal to that, which means 90 degrees to that, there's another wave. One wave is the electrical part, and the other wave is the magnetic part. So there are two components to electromagnetic radiation, the electrical component and the magnetic component. If you're a science major, you guys are going to be taking physics. And if you take physics, you guys are going to learn more about this right here. But the other characteristics about the light that we see, that we take for granted, is that if you break white light into its component, you get the different colors of the rainbow. And the different colors is because the wavelength are different. And so red light has a longer wavelength. It's got about 700 nanometers. Blue light is going to have a shorter wavelength. It's about 400 nanometers. And so that's just two components of the electromagnetic spectrum. If we take again white light and we run it through a prism, or it starts to rain like it has the past few days, and you go outside and the sun is behind you, it has to be behind you, because what the sun does is, if this is the sun, okay, and this is you, and these are raindrops in the atmosphere, then the light hits the raindrops, and then it breaks it up, and what you see in the horizon is the rainbow. And that's what a prism does, essentially, is it takes the white light here, it changes the angle by which it's going to diffract it, and because the white light is composed of different wavelength, and the different wavelengths are not the same, it sort of bends it, and then it separates the component. And so here you can see that red light has the longest wavelength, violet light has the shortest wavelength, and again, these are the components of the rainbow. Remember Roy G. Biv? That's at least how I learned the different colors of the rainbow back in 7th grade. Red, orange, yellow, green, blue, indigo, that's what I is, and violet. And there was an article recently about blue, and how blue was one of the most difficult color to obtain back in the early days, just because it was difficult to get that particular color. In fact, some native folks didn't have a word for blue because it was just taken for granted. Indigo was actually a more realistic color that was known back in the times, rather than blue. Anyway, that's for another story. Okay, what we have here is EMR, and EMR, electromagnetic radiation. Visible light is just a small fraction of radiation that we receive, that we take for granted. The other components of EMR are radio waves. So when you're listening to your favorite radio station, or you have an antenna, and back in the days you were receiving um, TV signals from those stations that would broadcast off the air, this is what we would have right here. It's basically wavelength that carries information. Microwave, your microwave oven, is a shorter wavelength. And even though it's out here, meaning it has very low energy, the reason why microwaves are very destructive is because the frequency of that microwave is the same frequency that vibrates water and provides energy to water. So when you're actually microwaving waving food, you are stimulating the water molecules in your food. And so that's why you generally make sure that your food has moisture in it in order for it to get warm. You don't generally want to put metals in there, because metals don't have water molecules, and then you just get a spark. Okay, infrared is lower energy, and that's just heat. And then we get the visible light, and then ultraviolet light. And you guys know that if you are exposed to ultraviolet radiation, that's why you put sunscreen. Then those types of radiation can actually cause damage to your skin, and it can cause cancer. The same with x-rays. That's why x-ray technicians wear a lead apron, because they're always in that radiation room, and there's going to be stray radiation. That's why they always hide behind a lead wall, so that they don't get exposed, because radiation exposure is a cumulative thing. um, when you're hit with it, the count goes up, and if you're hit with it so many times, then it can actually cause a lot of damage to your cells, and it can cause mutation, cancer. And then highest type of radiation that we know that we have here is gamma radiation, and you guys will see this more when we talk about nuclear chemistry. Okay, so again, visible light is just a very small component of electromagnetic radiation. And yet, through evolution, this is the type of light that we are most sensitive to. Our eyes has sort of evolved through the years so that we can see the different colors of the rainbow in this very, very narrow spectrum. Um, so when the Enlightenment years, remember the Enlightenment years? The Enlightenment years was when they start, um, humanity started to do a lot of scientific discovery, and that's because they started to ask very intelligent questions. Part of the Enlightenment years was Lavoisier, when he said that matter can't be created or destroyed; it can only be trans- uh, transferred, uh, transformed from one form to the other. Boyle started to question the Greek model of the atom. Shakespeare was in the Enlightenment years, so a lot of um, stimulation in terms of knowledge was brought up, and part of that stimulation was actually questioning nature and our universe. And part of questioning our universe was understanding what things were made out of around man's environment. And a couple of key scientists that made breakthrough in terms of this understanding the model of the atoms was Planck, Einstein, Bohr, de Broglie, and you guys will hear about them shortly here. But back in about maybe early 1900, a lot of maybe late 1800 to 1900, a lot of the physicists were so brazen that they thought that they discovered everything that needed to be known. Little did they know that that was just the tip of the iceberg. In fact, they understood electricity a little bit. They understood how the planets uh, orbit around the sun, and so they were thinking highly of themselves. One question that they had was the black body radiator, which you guys will cover in Chem 200, and why um, energy was such. They didn't understand that it could be broken up, radiation that could be broken up to different colors yet, and they didn't understand its true nature. But one of the things that came out of that was Planck's statement that energy is quantized. Now, what does that mean? Energy is quantized. Well, let me talk to you guys about matter. If you take matter and you chop it in half, then you can take the half and chop it down any further. And what happens is you get to a fundamental building block called the atoms. And different atoms represents the different elements. But basically, all matter around us is made out of different Lego pieces. Okay? So things that we can feel, tangible things that has mass and occupies volume, is made out of these fundamental building blocks. Well, Planck came to a realization that perhaps if matter can be broken up to individual pieces, can't energy be the same? Can't energy be broken down to simple pieces so that there's one fundamental piece? And what he did was he said that energy is also quantized, and he came up with this equation. This right here is a whole number. This right here is Planck's constant, and this right here is the frequency of the radiation. So that's Planck's equation. He basically said that matter, energy like matter, can also be quantized. There's an individual piece of energy that can't be broken down any further, and that individual piece is h nu. That's why we represent light later on as h nu, indicating that that's the photon of light that's being represented. Anyway, what we have here is this equation, and a bunch of other scientists, um, and I'm not going to go through the derivation, but they expanded on this particular equation. Remember, nu is the frequency, and frequency is basically the speed of light over the wavelength. And so that's what we have right here. And if you rearrange this equation, and so don't worry about the math, you find out that light has a mass component. Now, that's hard to accept, but that's what comes from the equation here. Anyway, um, what what goes on here is that light has mass, a relativistic mass, okay, comes from Einstein theory of relativity. And how we depict that now is through the fact that energy has a wave duality. A wave duality simply means that it has wave-like properties, it's got particle-like properties, and so we represent energy or radiation as photons. And to give you some sort of realistic um, illustration of what photons mean, it basically means it's got some sort of packet. So these packets represents the particle, and within each particle, there's some sort of radiation. So that's how I can describe, scientists sort of describes photons for you. Okay. And photons are the components of light that we can use to investigate the structure of the atom. So it, it goes back to say that if light or energy has particle like properties, that is, it can be quantized, can't matter also have wave like properties? That is, you and I actually have a wavelength associated with ourselves. And a scientist, a French scientist by the name of Louis de Broglie, this was his PhD thesis to kind of like resolve that. And he actually developed the equation that says that matter does indeed have wave-like properties. You and I have wave-like properties, the matter in us, and he did the derivation, and he actually, that was only his PhD work, but it allowed him to get a Nobel Prize. Okay, so you guys will actually cover this in much more detail in Chem 200. Here I simply present it so that you guys will be prepared for it when you get to Chem 200. Okay, um, and then this understanding of electromagnetic radiation and the atom gave us a new model, a new theory called quantum mechanics. Quantum mechanics is tries to explain the very, very small. Okay, it tries to explain uh, atoms, protons, electrons. And I remember when I was in grad school at Santa Barbara, one of the first course that they require PhD students to take is quantum mechanics. It's a whole year, and we do a lot of intense math, and we try to understand the behavior of atoms and particles. One of the theories of quantum mechanics is that you can be both here and there at the same time. If there's a wall separating you, there's actually a theory and equation that says that you can be in the other side. That sort of like goes beyond logic, but that's what the models of quantum mechanics tells you. It basically tells you tunneling theory. Now, after a whole year of taking quantum mechanics at Santa Barbara, when I finally did my last final exam um, in the spring semester, I was still as confused as when I started. It shows you how complicated this particular topic is. Okay, let me go ahead and move on. So let's go beyond that and talk about the atomic line spectrum. And you guys did this in your lab. Remember when you took different elements, and even the demonstration that I showed you when I had different elements and I put it in a watch plate, watch glass. I put a little bit of methanol in it and then I burned it. It gave you different colors. And that's because the different elements have different number of electrons. And the electrons are arranged in their orbital in different manner. And as you excite them, they start to go to, the electrons are promoted to a higher energetic state. And in the process of relaxing back down, that's what you see when you burn it. You excite it with the heat, and then the electrons come relaxing back down. They go back to their ground state, and that process release different radiation, different light. Okay, so again, because each element has a different number of electrons, each element have different type of electron configuration. Each element are going to have different ways in which the electrons relax back down to the ground state, and so they all have unique atomic line spectrum. So this is how it was discovered with the hydrogen atom. What they did was they took hydrogen and they radiated. You see how I have H nu here? And that sort of took the hydrogen molecule, broke the bond, but also caused the hydrogen molecule to go to an excited state. So basically what we have here is we put in energy, H nu, and we take the electrons that is on the hydrogen atom and we promote it to a higher energy orbital. Okay, that's called the excited state. Put that ES. As the electron, now this is the proton and this is the electron at a higher state. As the electron uh, starts to find its way back to the ground state, energy is released, and that energy is basically the different light that we see, characteristics of that particular element. Okay, so this is how we would do it. We would take, we would excite the element in here. We would try and focus the light that's coming out from that lamp down to a prism, and then the prism will break it up, the different colors of light, and this is what you see. Instead of the different colors of the rainbow, you see the specific wavelength of light due to the electrons dropping down from the excited state. Okay, and so let's move on here. So that model, that understanding was actually developed by Bohr, Niels Bohr. And when you look at it, when it was first introduced, it was basically the planetary model. And the reason why it's called the planetary model is because you have the nucleus here. That's where you find your protons and your neutrons. And then the electrons are basically orbiting the nucleus, just like the planets are orbiting the sun. Okay, and they have to go through fixed orbitals. So the electrons can only be found in fixed orbitals. They can't be found in between. In other words, the electron can't wander in between these spaces. It's like a hotel room. Okay, in a hotel room or a hotel, you have floors. You can be on the first floor, second floor, third floor, but you can't be in the first and a half floor. There's no such thing. Or that you can't be in the first and 3/4 floor. You can either be in 1, 2, 3, or 4. That is integer floors. So it's the same thing with these orbitals. Okay, you can be n equals 1, the first orbital shell, n equals 2, n equals 3. And actually, there's infinite number of shells here, but you can't be on 1.5, you can't be 2.5, you can't be 3 1/3. You have to be in fixed integers. So that's what Bohr's model the atom gave us. He said that the electron follows circular orbits around the nucleus, that the electrons only have certain size orbits, that's these different levels, called, and that's the quantum condition. Again, it tells you about unique discrete amount. Whenever you have discrete amount in whole integers, that's the quantum conditions. And electrons are allowed to go to higher orbitals. They can go to higher orbitals, but they can't go to orbitals that don't exist, like 3.5 or 3 3/4. They can go to 4, they can go to 3, but they can't go in between. Okay, so that's the model of the Bohr's atom, and that's part of quantum mechanics. So this is Niels Bohr, and he basically looked at the line spectrum, atomic line spectrum of the hydrogen atom, and he tried to decipher exactly how that how the model of the hydrogen atom can give rise to this atomic line spectrum. And what he did was he said that, okay, well, here it is. We have the nucleus right there, and you have all these orbitals that are allowed. N equals 1, N equals 2, N equals 3. It's like the different floors in a hotel. And what happens is that only the first floor, the first orbital, is occupied with electrons in its ground state, in its stable state. But when you hit hydrogen with enough energy, it can promote it to these higher energy states. And remember, we're not looking at just one hydrogen atom, we're looking at moles and moles of hydrogen atoms. So there's many ways. It's like going to a hotel and having hundreds and thousands of people go up into the different floors, okay? And then they occupy those floors. Remember, they can only go to like the second or third or fourth or maybe the 50th floor if it's a high enough hotel, but they can't go to the 50 and a half. There's no such thing. And then there's an emergency and everyone has to leave the hotel. They have to exit from the ground floor. Well, some of them might go from like the 58 to the 57 to the 56 to the 55. Okay, that's one pathway. Some of them might go from the 58 down to the 38 and then down to the ground floor. That's a different path. So each one of these individuals have different pathways to get down to the ground floor. And so that's exactly the analogy I'm trying to give you in terms of when these electrons are going to the excited states, they have different pathways of getting down to the ground floor to the most stable state, and that different pathways are represented by these different wavelengths of light, because these different pathways going down have different energies, and these energies are basically the radiation that comes out from the hydrogen atom, or for all elements uh, in that respect. And so Bohr figured it out. He figured out that, okay, well, this is the model that we have then. It has one proton, one electrons. It's got infinite number of um, shells, orbitals. And when we excite it, it populates these different shells. Remember, there are thousands of these hydrogen atoms, and one atom can populate number 38, another atom can populate 108. But eventually these electrons will all go down, and when they go down, they cascade the energy that that they absorb in going up. And so this is the line spectrum. Okay, so this is the atomic line spectrum, and you can see that these different lights actually corresponds to the different ways that the electron relaxes back down to the ground state. This is n equals 1. Okay, this is n equals 6 all the way up to n equals infinity. And again, the wavelength here that you see for hydrogen is due to the different relaxation, because these were discovered by unique scientists. These different lines over here are named after the scientists who discovered it. We have the Lyman series, where all the electrons from the higher energy state relaxes back down to the ground state, n equals 1. We have the bracket series, where all the electrons from the higher state relaxes to n equals 2. Of course, when the electrons are at n equals 2, they have to go back to the ground state. So you have an electron that is from the bracket series eventually going to n equals 2, that's second orbital. And then those electrons go back to the ground state, and they represent the Lyman series right here. Okay, so hopefully you guys have a better understanding of how the atomic line signature arises from the different atoms. And here's a better illustration. Okay, of course, Bohr started this idea of how the structure of the atom is created, but it didn't explain a lot of things. In fact, it explained only the hydrogen atom, or only those atoms or ions in which there's only one electron. If you have the hydrogen atom, it has one electron. If you have the helium ion, okay, so it's got two protons in the center, but only one electron outside. Why is it one electron? Because it's the helium ion. Remember, if it's a cation, it means that one electron is removed. If you have the lithium dication, that is three protons in the center and one electron out here, then the hydrogen model worked very well, because then you can calculate the energy of these electrons. And the reason why it was easy to calculate the energy of these electrons is because there's only one type of force that these electrons receive. They are attracted to the proton, the nucleus, and so it's a one-to-one correspondence. As soon as they did elements with two or more electrons in them, then you have complications, because not only do you have the attraction between one electron and the nucleus and another electron with the nucleus, but you also have different intermolecular, not intermolecular, but different energy um, fields between the two electrons that are constantly moving. And so what happened was that the math model that they developed when they started to look at atoms with more than two electrons started to break down. In fact, it broke down miserably. And so a new theory had to be introduced, a new theory that explains the energy for elements with more than one electron. And that theory was the Schrodinger wave equation. Okay, the Schrodinger wave equation. So we'll talk about the Schrodinger wave equation shortly, but again, this is a summary of the atomic line spectrum. And so now, hopefully, you understand why we can look at the sun, and based on the atomic line signature, we can say what elements are in the sun. We can say that it's mostly helium and hydrogen, because we can see the line signature from the sun. And we can say that, yeah, it's made out of hydrogen and helium and other elements in there. We can look at the moons of Jupiter and say that it's got water molecules, because not only does atom have atomic line signature, but molecules also have molecular line signature. That's because molecules have electrons, and the electrons are housed in these orbitals, and the orbitals can be excited to a higher state and relax back down to the ground state. So molecules are nothing more than clusters of atoms, okay, that are held together through bonds, but they all have electrons in it. And depending on how you excite the electrons in these molecules and how they relax back down to the ground state, they too give unique molecular line signature that's unique for that particular chemical. Water has a unique line signature, and so we can tell whether a planet has water in its atmosphere or methane in its atmosphere, etc. Okay, so yeah, move on. So let's go back and understand exactly what the new model is. And again, this is just sort of like an introduction for the next section, but we have relative energy, shells, and orbital. You got to understand the difference between orbitals and shells, and you might think that they're the same, and yes, they are sort of the same, but it's a very complicated picture. Okay, we can think of an atom in terms of the nucleus. Let me change my pen here. And the nucleus is where you have the protons and the neutrons, okay? And then you have these orbitals. And these orbitals, n equals 1, is where the electrons are housed, okay? N equals 1, n equals 2, n equals 3. But these orbitals are actually a very complicated array. It's kind of like taking a hotel. I always like to go to the hotel analogy, because it sort of gives you a visual of how the structure of the atom works. So we have the first floor, and in the first floor, there's rooms in there. In fact, there's only one room in there, and we can call that the suite. And then on the second floor, there's two types of room. We have like suites and penthouse, but that's found in the second floor only, suite and penthouse. In the third floor, we have three types of room: a suite, a penthouse, and say a dormitory. Okay. And then in the fourth floor, we have four types of room. We have a suite, a penthouse, a dormitory room, and then a flat. I think you get an idea of what I'm doing. These S, P, D, and F are the name of the orbitals in each of the levels of an atom. Okay. And each of these have different, what we call quantum numbers. And so just sort of accept it for now, and we'll do more investigation next time. But that's basically how the model of the atom is developed. It's actually not just concentric spheres, it's concentric spheres in which there's complications involved. So what we have is the n equals 1, we have an s orbital. These are called orbitals, okay? These are called shells. The n equals 1, 2, 3, 4. These are called shells. Okay, it's like an onion. We have the first shell, second shell, third shell, etc. But within each of these shells, we have something called orbitals. All shells will have something called an s orbital. That's this right here. But only starting on the second floor, you have the p orbitals. Okay, starting on the third floor, you have, or the third shell, you have the d orbitals. Starting on the fourth, you have the f, and then it goes on from there. Okay, we don't have atoms that starts to occupy the g orbital and h orbital, but if we had atoms that had that many number of electrons, then we would certainly call those orbitals g and h, etc. Okay, so hopefully you can see again the picture of the atom that you guys will eventually have to understand in order to digest quantum, a little bit of quantum mechanics, and to digest um, electron configuration at a deeper level. Okay, and the guy who developed this idea was Erwin Schrodinger, and he basically said that electrons are not particles. Okay, they have particle-like properties and they have energy-like properties. So it's not good to define an electron, this is the nucleus, as a particle, thinking that it can move from one shell to the other. In fact, what we need to do to be more realistic is to describe the electron as a cloud or a probability function. Okay, probability. This is the Greek letter psi. And so what he did was he introduced the electron cloud. And the electron is not a particle, it's not a wave, it's a probability. And that's what's difficult to grasp when you're a beginning chemistry student, is because we want to think of things in terms of things we can understand. Once they say a particle is a wave function, that's out of our realm. And that's probably why I struggled with quantum mechanics when I was taking it in graduate school. Today, I sort of accept it, but it's really beyond my reach in terms of really understanding the intricacy of that model. And so I leave it to smarter people to figure that out. Okay. What we're trying to do here is give you at least the foundation so you know how we start to develop the the model of the atom and why certain results come out when we do scientific experiments dealing with atoms. So, and this is one of the things that we take for granted, fireworks, and it actually is can be explained by um, quantum mechanics in terms of what's going on. So let's take a look at this real quick. Um, so what we have here is, let's see why. It's basically the chemistry of fireworks has to do with, again, the electrons being promoted and then relaxing back down. So if you have a chance, the audio on this is not working, probably because I don't have my speaker on. But if you have a chance and you can go to the PowerPoint, then you guys can take a look at that, or just do a Google search on the chemistry of fireworks. Okay. So, and what about the stars? How can we figure out what elements the stars are made of? Well, again, it has to do with the atomic line signature from the stars. And we can look at stars or whole galaxies and figure out what are the components there. And this is just um, a snippet of the different types of elements that they've sort of come to realize exists out there, just based on the atomic line signature from um, uh, stars and other mass galaxies that are out there. So this is just a history on that. Okay, so you guys can take a look at that. For those of you who want to go into astronomy, there's a lot of chemistry in astronomy, believe it or not. And then, of course, this is just a summary of what we talked about. And again, the flame test that you did gives you a more detailed understanding of what's going on. So I'm going to quit there, okay? Uh, just because I don't want to go into the next section, which is really more complicated. I want to make sure until you guys don't have to worry about the midterm, because probably some of the stuff that I'm talking here, you guys are hearing it, but not really being involved just because you have other things to worry about. But I'm going to stop here in terms of this um, presentation, and then I'll continue with chapter 9 next time. So if there's questions, please let me know, and I'll stop the lecture here and I'll finish up your midterm so that it'll be ready to be released tonight. For those of you in lab, around 3 o'clock, I'll be in the lab canvas with Zoom, and then I'll give you guys an overview of what your midterm and your lab practical is about. Yeah, I agree, James. It's a lot more difficult to learn online. Again, it's weird because the first thing that happens is I'm finding myself also kind of talking to myself in my office at home, and I can't gauge whether you guys are understanding these things. Okay, um, hopefully at least through these sessions you're understanding more than if it was just static and you just had to read the PowerPoint and the text. But hopefully it will make it'll be a lot more you get more information as if we weren't having these sessions. Okay, but yeah, don't worry about chapter 9. Chapter 9 is not until your next quiz, but certainly it is difficult, and that's why I post the videos of our session so that you can go in and take a look at it and look at it in more detail and rewind it if you can. And then, of course, because and it's difficult because that means that you guys have to take the time to Google these information and look up some certain information if you have some sort of questions about certain concepts. Okay. Uh, well, I wouldn't worry about your grade. All my classes are sort of like curve, so you're really just competing against your classmate. Okay, if you're doing well on class and you're doing well relative to your classmate, it is a curve class, and I understand the circumstance that everyone is, and if the highest is like an 85, then that's the A. Okay, we'll have to go with that. We got to make concessions in these difficult times, and if you make in an effort, if you do work on the things, um, if you're having a difficulty understanding these materials, please send me an email, make arrangement to see me in Zoom, or just try and reach out, and I'll try and explain things. And certainly In terms of your attendance, yes, I always have a docket in Zoom because it has the transcript and it lists all the people who have participated in it. And again, it the, you guys, if you're really having difficulty, remember that the drop deadline is May 8th. So take the midterm, take your next quiz, and what I will do is I will give you an overall rating of how you stand relative to your classmate. That is, give you a histogram of your points to date relative to your classmate so you know where you stand. Okay. So, yeah, it is very frustrating. I agree with everyone here. And we're getting to a topic, quantum mechanics, where it's even more difficult based on just listening and seeing a PowerPoint slide. Okay. So I think everyone, even my advanced class, are showing the same frustration. So I hear you, and I think all your professors, your instructors, also hear you, and we'll try and we will make some sort of accommodations for that. Okay, so please, when you are studying so I understand and make an adjustment and takes time. And yeah, it does take time. The lecture that I give are actually the same type of lecture I would give on campus, but again, it's difficult because you guys are staring at the screen rather than at me, and I can't see you guys, and I can't see your facial expression. Anyway, I'm glad that you guys can air your frustration, and I'll certainly make it known to our chair and our administration in terms of that. Okay, so I'm gonna go ahead and call it quits. But certainly, if you want to vent more, go to the discussion room and tell me your frustration in terms of that. That way, I can relay it to the admin in terms of what's going on. Okay, so I'll see you guys in lab, and I will be there around 3 o'clock, about half an hour. Okay, thanks, and thanks everyone for attending, and you guys stay healthy. Bye.